ಎಲ್ಲ ಚೈನೀಸ್ ಐಟಮ್ಸ್ ಅಲ್ಲ ಮೇಡಮ್. ಬೇಡ ಅಂತ ಹೇಳಿದ್ರಲ್ಲ ಹೆಚ್ಚು. ಆಮೇಲೆ ನನ್ನನ್ನು ಕರೆದು ಆನ್ಲೈನ್ ಗೇಮ್ನಲ್ಲಿ ಯಾರು ಅದಕ್ಕೆ ಇಲ್ಲಿ ಎಕ್ಕೋ ಬರ್ತಿದ್ದು ಅವ್ರು ಪ್ರಿನ್ಸಿಪಲ್ ಜಾಯ್ನ್ ಆಗುತ್ತೆ ಹಾಕಿದ್ದೆ, ಅದು ಡಬಲ್ ಬಂತಲ್ಲ, ಇಲ್ಲಿಂದ ಹೋಗುದು ಅಲ್ಲಿಂದ ಬರುತ್ತೆ.
ಇಲ್ಲಿ ಬಂದಿದೆ.
ನಾನು ಸರಿ ಮಾಡಿದ ಆದ್ರೆ ಕರೀತೀನಿ ಮ್ಯಾಮ್.
ಮೈಕ್ ಯೂಸ್ ಮಾಡೋದೇನು ಬೇಡಲ್ಲ. Myself Babita, pursuing PhD under this. My dissertation work is on investigation on boundary layer flow and heat transfer effect on Newtonian and non-Newtonian fluids. Outline of my presentation. Chapter 2 to Chapter 7. Non-Newtonian fluids. Publication, research paper presented in national references, finally acknowledgement. Chapter 1 is introduction. Fluid mechanics is the branch of science that deals with the study of fluids, behavior of the fluids which are at rest as well as motion. Further, it divided into three divisions. One is fluid statics. It deals with the study of behavior of fluids which are at rest, and next one is fluid kinematics. It deals with the study of behavior of the fluids which are in motion where pressure forces are not considered, and last one is fluid dynamics. It deals with the study of behavior of fluids where the pressure forces are considered. And in our day-to-day life, we can find the several applications of the fluid mechanics. For example, in wind turbines, in artificial hearts, breathing machines. Okay, ma'am. Breathing machine, artificial hearts, dialysis system, etc. Okay. The next boundary layer flow. So boundary layer flow is a very thin layer of a flowing fluid in the vicinity of an adjacent solid surface where the viscous effect is significant. For example, in the Earth atmosphere, the air near to the ground, it forms an atmospheric boundary layer, and the air layer is affected by the moisture, heat or momentum transferred to or from the surface. The concept of the boundary layer is first introduced by L. Prandtl in the year 1904. According to his theory, whenever a fluid flows past a stationary solid surface, then it will be divided into two regions. A very thin layer close to the solid surface, that's called boundary layer region. In this region, the viscosity effects are significant, and outside this region, the viscosity effect can be neglected. Same thing? Okay, ma'am. The same thing we can observe in this figure. Newtonian and non-Newtonian fluids. A real fluid is... Okay, ma'am. A real fluid is said to be Newtonian. A shear stress is directly proportional to the rate of shear strain or velocity gradient. That's called Newtonian fluid. In case of Newtonian fluid, viscosity remains constant no matter the amount of shear is applied for a constant temperature. And moreover, Newtonian fluid satisfies the Newton's law of viscosity that's given by equation 1. And for some example for the Newtonian fluid is water, benzene, alcohol, mineral oil, etc. And non-Newtonian fluids do not obey the Newton's law of viscosity. Some examples of non-Newtonian fluids are paste, gel, blood, saliva, etc. Transfer. Heat transfer is a form of... Okay, ma'am. Okay. So next, transfer is the form of energy that can be transformed from one system to the another system by the virtue of temperature difference. The science that deals with the determination of rate of such energy transform is heat transfer. Heat transfer is called... Okay, ma'am. ಒಂದೆರಡು ಮೂರು ಹೇಳಿ ಎಕ್ಸೆಟ್ರಾ ಹೇಳಿ. Okay, ma'am. In our study, we consider skin friction, heat and mass transfer rate. Skin friction or friction drag is estimates the viscous shear stress exerted on the wall. It is given by equation number 2. Nusselt number or heat transfer rate, it is the ratio of heat flux per unit area to the excess temperature, that is TW minus T infinity, the surface over the temperature T infinity of the free stream, that is given by equation number 3. Then mass transfer rate, that is defined in terms of Sherwood number, it is the ratio of mass convection to the mass diffusion, and it is given by equation number 4. This is introduction. This time introduction al hakirodu. Chapter 2, impact of heat and mass transfer on mixed convective flow of nanofluid through a porous medium. So in this study I have considered, ma'am, we have used madla jasti. We are going to deal with the mass transfer characteristics of the nanofluid. Nanofluid is the mixture of nanometer size solid nanoparticles in the base fluid. Commonly okay. Okay, ma'am, sorry. My first work is on impact of heat and mass transfer on mixed convective flow of nanofluid through porous media. So nanofluid is a mixture of nanometer size. Adela. ಆ ಥರದ ವರ್ಡ್ನ nanofluids are the mixture of nanometer sized solid particles in base fluid. Commonly used nanoparticles are oxide ceramics, carbon nanotubes, metal and metal carbides, nitrides, etc. And commonly used base fluids are water, kerosene oil, other lubricants and polymer solutions, etc. And some of the applications of the nanofluids can be observed in nuclear reactors, cooling of heat exchanging devices, nano drug delivery, cancer imaging, etc. So in this study, the fluid flow is unsteady, laminar, mixed convective flow of nanofluid over an infinite vertical plate, which is stationary or moving. Okay. ಮಾಡ್ಬಿಟ್ಟು ಇಲ್ಲಿ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡೋಣ ಅನ್ಕೊಂಡಿದ್ದೀನಿ ಮ್ಯಾಮ್ ಜಾಮಿಟ್ರಿ. ಹಾಂ ಮ್ಯಾಮ್ ಇದನ್ನು ಕಾನ್ಫಿಡೆಂಟ್ ಆಗಿ ಹೇಳ್ತೀನಿ. ಸೊ ದಿಸ್ ಇಸ್ ದ ಜಾಮಿಟ್ರಿ ಆಫ್ ದಿ ಫ್ಲೋ. ಇನ್ ದ ಕಾರ್ಟೀಸಿಯನ್ ಕೋಆರ್ಡಿನೇಟ್ ಸಿಸ್ಟಮ್ ದ ಪ್ಲೇಟ್ ಈಸ್ ಕನ್ಸಿಡರ್ಡ್ ಅಲಾಂಗ್ ದಿ ಎಕ್ಸ್ ಡೈರೆಕ್ಷನ್. Here we consider the Cartesian coordinate system. In this Cartesian coordinate system, the plate is considered along the x direction, which is vertically upward direction, and y is normal to the x direction, and uniform radiative heat flux and uniform magnetic field are applied normal to the flow field. And the flow is unsteady. When initially the plate is at rest with the constant temperature T infinity and constant concentration C infinity. When T is greater than 0, the temperature and concentration lower or rise to Cw and Tw. These are the governing equation for the present model. By equation number 5, 6 and 7. Momentum equation 6 is the effective properties of the nanofluids are computed by using these following relations. And And in this study, we considered water as a base fluid and copper as a nanoparticle, and thermophysical properties are tabulated in this table. The governing equations are subjected to the initial and boundary condition mentioned in equation number 8. And radiative heat flux is approximated by using the exponential form. Okay, ma'am. Radiative heat flux is approximated by using the Rosalind approximation, and it is given by equation number 9. Radiative heat flux in the thermal energy equation, we obtained equation 10. The non-dimensional quantities in this study is mentioned in equation 11. The non-dimensional form of the governing equation, that is momentum, temperature and concentration equation, is given by equation number 12, 13 and 14, and 15 is the non-dimensional form of the boundary conditions. These are the constants which are involved in the non-dimensional form of the governing equations. So in order to solve this problem, we use the one of the strongest method, that is Laplace transform technique. So apply the Laplace transform technique to the governing equation. We obtain the equation 16, 17, 18 and the initial and boundary condition 19. But in order to solve the solution, in order to obtain the solution for the velocity equation, we consider two types of the pressure gradient. One is constant pressure gradient, another one is linear pressure gradient. Okay, ma'am. Here we consider two cases of the pressure gradient. One is constant pressure gradient. Okay, ma'am. Then solution of temperature and concentration is given by equation number 20 and 21. Then the constant pressure gradient. When we consider the constant pressure gradient in the velocity equation, that reduces to equation number 22. The solution, after applying the inverse Laplace transform, we get the solution for temperature, concentration and velocity, that is given by equation number 23, 24 and 25. Then case 2, linear pressure gradient. Similarly, we can consider the linear pressure gradient in the governing equation, so that is reduced into the equation number 26. Then the solution of velocity profile is given by equation number 27. After applying. So these are the constant involved in the solution. In order to compute the friction drag, heat and mass transfer rate, so the friction drag at the boundary is given by equation number 28. For constant pressure gradient, the friction drag at the surface is given by equation number 28, and the screen friction at the boundary for linear pressure gradient is given by equation number 30. The heat transfer rate at the boundary is given by equation number 31. The mass transfer rate at the boundary is given by equation number 32. So these are the constant which involved in the heat and mass screen friction Herold numbers. Resultant discussion. The effect of magnetic parameter and velocity distribution. As magnetic parameter increases, velocity decreases because there exists the Lorentz force. Lorentz force is a resistive type of force having the tendency of decreasing the motion of the fluid. This result to decreasing the fluid velocity. Similarly, for case 2, the same phenomena will exist. The effect of porous parameter on velocity profile. As porous parameter increases, velocity profile will decreases, because increase in porous parameter increases the flow resistance, that decreases the velocity field. We observe the same phenomena in the case 2 also. The effect of Solital-Grashof number on velocity profile. As Solital-Grashof number increases, velocity profile increases, because Solital-Grashof number is the ratio of the species buoyancy force to the viscous hydrodynamics force. As Solital-Grashof number increases, hydrodynamics force decreases, which thickens the momentum boundary layer. Automatically, the velocity of the fluid increases. The same phenomena will observe for the case 2. The effect of nanoparticle volume fraction and velocity profile. As nanoparticle volume fraction increases, velocity will decreases, because when nanoparticle volume fraction increases, the friction force within the fluid also increases. Due to that, the fluid motion decreases, so that velocity will decreases. Okay, velocity decreases. Velocity decreases. For case 2. ಚೇಂಜ್ ಮಾಡ್ತೀನಿ ಮ್ಯಾಮ್, ಪ್ರಾಕ್ಟೀಸ್ ಮಾಡ್ತೀನಿ. ಇಲ್ಲ ಮ್ಯಾಮ್, ಇನ್ನೂ ಪ್ರಾಕ್ಟೀಸ್ ಮಾಡ್ತೀನಿ ನಾನು. So the effect of chemical reaction parameter on concentration, the effect of chemical reaction parameter and ಇಲ್ಲ ಮ್ಯಾಮ್, ಇಲ್ಲ ಮ್ಯಾಮ್, ಪ್ರಾಕ್ಟೀಸ್ ಮಾಡ್ತೀನಿ. Effect of chemical reaction parameter and Schmidt number on concentration profile. As chemical reaction parameter and Schmidt number increases, concentration profile decreases, because higher values of the chemical reaction parameter leads to the fall in the chemical molecular diffusivity, that leads to fall in the concentration profile. Has increase in the Schmidt number corresponds to a lesser solutal diffusivity, which allows a shallower penetration of the solute effect. As a consequence, there is a decrease in the concentration as the Schmidt number increases. The effect of nanoparticle volume fraction and temperature profile. As nanoparticle volume fraction increases, temperature within the fluid also increases, because as nanoparticle volume fraction increases, thermal conductivity of the fluid also increases. Automatically, thermal boundary layer thickness increases, that leads to increase in the temperature profile. And moreover, nanoparticle volume fraction plays an essential role in the improvement of the heat characteristic of the fluids. In many industrial process, temperature can be controlled by the nanoparticle volume fraction. The effect of Prandtl number on temperature distribution. As Prandtl number increases, temperature profile decreases, because larger value of the Prandtl number has low thermal conductivity, so that result in less heat penetration. Okay. Okay. Variation of skin friction for various values of the physical parameters. As skin friction increases with an increase in the time, thermal Grashof number and solute. Okay, ma'am. Thermal Grashof number and solute Grashof number, where opposite behavior is noted for influence of magnetic parameter and porous parameter. Try ಮಾಡ್ತೀನಿ ಮ್ಯಾಮ್. Variation of Nusselt number for various values of Prandtl number. Okay, ma'am. Table explains the variation of Nusselt number for various values of Prandtl number and time. As Prandtl number increases, heat transfer rate also increases. As time increases, heat transfer rate decreases. From this table, one can observe that the mass transfer rate in the fluid is increasing function of Smith number and chemical reaction parameter, but decreasing function for time. The overall conclusion for this chapter is, increasing the volume fraction of nanoparticles leads to a significant effect on velocity, temperature, Chapter 2, Analysis of heat and mass transfer on natural convective flow of fractional nanofluids with different nanoparticles, base fluids and shapes of nanoparticles with thermal radiation. In chapter 2, we can... Title chapter... Chapter ರೆಡ್ಡೇ ಇರಲಿ ಅಲ್ಲ. Chapter we consider, in the previous chapter we consider only nanofluid, that is water based copper nanofluid. In this chapter we consider three different copper nanoparticles, that is copper, copper oxide and silver, different base fluids, water, sodium alginate and ethylene glycol, and four different shapes of nanoparticles, that is blade, brick, platelet and cylinder. Along with these things, instead of ordinary integer model, in this chapter we consider fractional order model. Fractional calculus. In case of dn f of x by dxn, if n is a natural number, that comes under the ordinary differentiation. If n becomes a real number or a complex number, that comes under the fractional differentiation. n fraction real number complex number ಆದರೆ ಅದು fractional calculus ಗೆ ಬರುತ್ತೆ ಮ್ಯಾಮ್. ಹೌದು ಮ್ಯಾಮ್. ಮ್ಯಾಮ್ ರಿಯಲ್ ಅಲ್ಲಿ ಎಲ್ಲ ಬಂದ್ಬಿಡುತ್ತೆ ಮ್ಯಾಮ್. ಹಾಂ ಮ್ಯಾಮ್ ತಗೋಬೋದು, ಬರುತ್ತೆ ಮ್ಯಾಮ್. ಮ್ಯಾಮ್ ಓನ್ಲಿ ನ್ಯಾಚುರಲ್ ನಂಬರ್ ಇದ್ದರೆ ಆರ್ಡಿನರಿ ಕ್ಯಾಲ್ಕುಲಸ್ಸಿಗೂ ಆರ್ಡಿನರಿ ಡಿಫ್ರೆನ್ಸಿಯೇಷನ್ ಮ್ಯಾಮ್. ಹಾಂ ಮ್ಯಾಮ್, ಅದರ್ ದನ್ ನ್ಯಾಚುರಲ್. ಹಾಂ ಮ್ಯಾಮ್, ಕಾಂಪ್ಲೆಕ್ಸ್ ಬರುತ್ತೆ. ಚೆಕ್ ಮಾಡಿದ್ದೀನಿ ಮ್ಯಾಮ್ ಅದರ ಡೆಫಿನೇಷನ್ನ. ಶೋರ್ ಮ್ಯಾಮ್. ಮ್ಯಾಮ್ ಇವಾಗ ರಿಯಲ್ ನಂಬರ್ ಇಸ್ ದ ಲಾರ್ಜೆಸ್ಟ್ ಸೆಟ್ಟು. ರಿಯಲ್ ನಂಬರಲ್ಲಿ ನ್ಯಾಚುರಲ್ ನಂಬರ್ ಎಕ್ಸಿಸ್ಟ್ ಆಗುತ್ತೆ, ಬಟ್ ನ್ಯಾಚುರಲ್ ನಂಬರಲ್ಲಿ ರಿಯಲ್ ನಂಬರ್ ಎಕ್ಸಿಸ್ಟ್ ಆಗಲ್ಲ ಮ್ಯಾಮ್. ಬಟ್ ಇವಾಗ ಅದರ್ ದನ್ ಇನ್ ನ್ಯಾಚುರಲ್ ನಂಬರ್ಸ್ ಅಂತ. ಹಾಂ ಮ್ಯಾಮ್, ಹೌದು. ಹೌದು ಮ್ಯಾಮ್. ಎಸ್ ಮ್ಯಾಮ್. ಗೂಗಲ್ನಿಂದ ತಗೊಂಡೆ ಮ್ಯಾಮ್ ಇದನ್ನು. ಆಲ್ಫಾ ಇಸ್ ಈಕ್ವಲ್ ಟು 1 ಆದರೆ ನಮ್ಮ ಮಾಡಲ್ನೇ ನಾವು ಇಂಟಿಜರ್ ಮಾಡಲ್ ಹೇಳ್ತೀವಿ ಮ್ಯಾಮ್. ನಾವು ಕಂಪ್ಯಾರಿಟಿವ್ ಸ್ಟಡಿಲಿ ಅದನ್ನು ಮಾಡಿದ್ದೀವಿ. ಹಾಂ ಮ್ಯಾಮ್ ಮಾಡಿದ್ದೀವಿ. ಹಾಂ ಮ್ಯಾಮ್ ಇಂಟಿಜರ್ ಮಾಡಲ್ ಅಂತಲೇ ಹೇಳ್ತೀವಿ. ಸ್ಪೆಷಲ್ ಕೇಸ್ ಅಂತ ನಾವೇ ಮೆನ್ಷನ್ ಮಾಡಿದ್ದೀವಿ ಮ್ಯಾಮ್ ಅದನ್ನು. ಇಲ್ಲ ಮ್ಯಾಮ್, ಅದು ಇಂಟಿಜರ್ ಮಾಡಲ್ ಆಗೇ ಇರುತ್ತೆ ಅದು. ಮಾಡಲ್ ಅಂತಾನೆ ಹೇಳ್ತೀವಿ ನಾವು. ಫ್ರಾಕ್ಷನ್ಗೆ ಬರಿಬೋದು ಮ್ಯಾಮ್. ಹಾಂ ಮ್ಯಾಮ್, ನನ್ನ ಕ್ವಶನ್ ಅರ್ಥ ಆಯಿತು ಮ್ಯಾಮ್. Study, we consider the following points. So, unsteady laminar natural convective flow of different fractional nanofluids over an infinite vertical plate. So, this is the geometry of the flow. In the Cartesian coordinate system, the plate is along the x direction, which is vertically upward direction, and y is normal to the plate. The radiative heat flux applied normal to the flow direction. Initially, the plate is at rest with constant temperature T infinity. When time is greater than 0, it starts to the temperature lower or rise to TW. So the governing equation for the present model, equation 33 is the momentum equation and 34 is the temperature equation. The present problem is divided into two sections. So in section A, we have studied about the heat transfer analysis of 3 different nanofluids. So that is copper, copper oxide and aluminium considered as a nanoparticles with water as a base fluid with a non-uniform thermal radiation. In section B, we consider 3 different base fluids, water, sodium alginate and ethylene glycol with 4 different shaped copper nanoparticles, that is the blade, brick, platelet and cylinder. So the governing equations are subjected to the initial condition that is given by equation number 35. In the equation number 35, U is equal to G of T. We are again considering 2 types of the boundary condition. Okay, ma'am. In initial and boundary condition, U is equal to G of T. Again, we consider two cases of the velocities, that is linear velocity and constant velocity. Equation 36 gives the non-dimensional quantities of the present model. So thermo properties. Okay. The non-dimensional form of the governing equation is given by equation number 37 and 38. So these are the quantities, these are the constants involved in the non-dimensional form of the governing equations. So equation 39 is the non-dimensional form of the initial and boundary condition. So here we are replacing the integer order model by the fractional order model. Only the time derivative is replaced by the fractional order model, that is C d alpha t is dou u by dou t. 40. Okay, equation 40 and 41. Here C d alpha t is the capital time fractional derivative, that is given by equation number 42. So in order to obtain the solution, first we computed the solution for the temperature. By applying the Laplace transform technique, we obtained the solution for the temperature, that is given by equation number 44. We express the solution of temperature in terms of one of the special function, that is right function. So velocity, first case is constant velocity. So G of t is A naught. Apply the Laplace transform. Apply the Laplace transform to the governing equation and corresponding initial and boundary condition. We get the equation number 45. After solving equation number 45, we will getting the equation 46. After eliminating constant C1 and C2 using the initial and boundary condition, we get the equation 47. By using the convolution theorem, we get the equation 48. The simplification form of equation 48 is given by 49. This is the solution of velocity. Okay. The velocity solution is represented in equation 49. So, the case 2, linear velocity is considered. The form of linear velocity is given by g of t is equal to a naught plus b naught t, where a naught and b naught are constant. By using the same mathematical technique in case 1, we obtained the solution for velocity profile that is given by equation number 50. So, the skin friction and Nusselt number is obtained, the skin are computed, and we obtained the skin friction and Nusselt, skin friction for at the boundary for constant velocity is given by 51, for linear velocity is given by 52, and mass heat transfer rate is given by equation number 53. So section B, in section B, here we consider the different thermophysical properties model. First one is thermal conductivity of the nanofluid. Thermal conductivity of the nanofluid is given by the Hamilton-Crosser model, which is given by equation number 54. When n is equal to 3, that is the spherical, when n is equal to 3, the above model is reduced to the equation number 55. So n is equal to 3, the shape of the nanoparticle becomes the spherical shape of the nanoparticle. Then viscosity of the nanofluid is given by equation number 56. The sphericity and constant A1, A2 are of the different shapes of the nanoparticle is tabulated in this table. These are the thermophysical properties of the base fluid and nanoparticle. Nanoparticle used in this study. The governing equation are subjected to the initial and boundary condition that is given. Same procedure barutte ma'am. Once again same. Okay. The non-dimension form of the governing. The effect of nanoparticle volume fraction and velocity distribution has nanoparticle volume fraction increases, velocity decreases, because as nanoparticle increases, the friction force within the fluid also increases. The velocity of the fractional nanofluid reduces with increasing values of the alpha also. This is for section B. The effect of different shapes of different nanoparticles on velocity distribution. Fractional nanofluids involving different nanoparticles experiences more velocity in the order silver, copper and copper oxide because of the density of the nanoparticles. As density of the nanoparticle increases, corresponding velocity also increases. The effect of different shapes of nanoparticles on velocity distribution. The maximum velocity is decreases in the order platelet, cylinder, brick and blade respectively. The effect of different base fluids on velocity distribution is discussed in this figure. Maximum velocities are in the order of CuH2O, CuSa and CuEge because viscosity increases, velocity decreases. Here, water-based nano. ಹಾಗೆ ಹೇಳ ಮ್ಯಾಮ್. ಓಕೆ ಮ್ಯಾಮ್. ಮ್ಯಾಮ್ ನನಗೆ ಒಂದು 2 ಕಡೆ ಡೌಟ್ಸ್ ಇದೆ, ಅದನ್ನೊಂದು ಓಕೆ ಮ್ಯಾಮ್. ಪ್ರಾಕ್ಟೀಸ್ ಮಾಡ್ತೀನಿ ಮ್ಯಾಮ್. ನಾನು ತೋಸ್ಟ್ ಇಲ್ಲ ಮ್ಯಾಮ್, ನಾನು ಪ್ರಾಕ್ಟೀಸ್ ಮಾಡ್ತೀನಿ, ಚೆನ್ನಾಗೇ ಕೊಡ್ತೀನಿ. ಇಲ್ಲ ಮ್ಯಾಮ್, ಚೆನ್ನಾಗೇ ಕೊಡ್ತೀನಿ. ಇಲ್ಲ ಮ್ಯಾಮ್, ನಾನು ನೀಟಾಗಿ ಮಾಡ್ತೀನಿ. ಇಲ್ಲ ಮ್ಯಾಮ್, ಮಾಡ್ಕೊಳ್ಳೋಣ ಮ್ಯಾಮ್. ಇದು ಲಾಸ್ಟಲ್ಲಿ ಪೇಪರ್ ಪ್ರೆಸೆಂಟೇಷನ್ ಇರಲ್ಲ ಬೇಡವಾ ಅಂತ, ರಿಸರ್ಚ್ ಪೇಪರ್ ಪ್ರೆಸೆಂಟೆಡ್ ಇನ್ ವೇರಿಯಸ್ ಕಾನ್ಫರೆನ್ಸಸ್. ಓಕೆ ಮ್ಯಾಮ್. ಎಸ್ ಮ್ಯಾಮ್, ನೀವು ಹೇಳ್ತಾ ಇರೋದು ಅರ್ಥ ಆಗ್ತದೆ. ಓಕೆ ಮ್ಯಾಮ್. ಮ್ಯಾಮ್, ನಂದು ಜಾಮಿಟ್ರಿ ಥ್ರೂಔಟ್ ಪ್ರಾಬ್ಲಮ್ಮು ಸೇಮ್ ಬಂದುಬಿಡುತ್ತೆ. ಲೈಕ್ ಇವಾಗ ಫ್ಲೂಯಿಡ್ ಪ್ರಾಬ್ಲಮ್ಸು ಚೇಂಜ್ ಆಗುತ್ತೆ. ಅದು ಸೇಮ್ ರಿಪೀಟ್ ಆಗ್ತಾ ಇದೆ ಮ್ಯಾಮ್ ಥ್ರೂ ಔಟ್, ಅದಕ್ಕೆ. ಎಸ್ ಮ್ಯಾಮ್. ಆಲ್ಮೋಸ್ಟ್ 6 ಚಾಪ್ಟರ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಇದೆ ಮ್ಯಾಮ್. ಆ ಚಾಪ್ಟರ್ ಯಾವ್ದು ಇಂಪಾರ್ಟೆಂಟ್ ಅದು. ಎಫೆಕ್ಟ್ ಆಫ್ ನ್ಯಾನೋ ಪಾರ್ಟಿಕಲ್ ಫಸ್ಟಲ್ಲೂ ಹೇಳ್ತೀನಿ, ಸೆಕೆಂಡಲ್ಲೂ ಹೇಳ್ತೀನಿ, ಥರ್ಡ್ ಚಾಪ್ಟರ್ ಅನ್ಸ್ಟಡಿ ಎಲ್ಲದರಲ್ಲೂ ಇದೆ ಮ್ಯಾಮ್ ನನಗೆ. ಟೋಟಲ್ 7 ಚಾಪ್ಟರ್ಸ್ ಇದೆ. ಮಾಡ್ಕೊಳ್ತೀನಿ. ಓಕೆ ಮ್ಯಾಮ್. ಇಲ್ಲ ಮ್ಯಾಮ್, ನಾನು ಚೆನ್ನಾಗೇ ಮಾಡ್ತೀನಿ. ಓಕೆ. ಚಾಪ್ಟ್ರಲ್ಲಿ ನ್ಯೂಮರಿಕಲ್ ಪ್ರೊಸೀಜರ್ ಫುಲ್ಲು ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡಬೇಕಾ ಅನ್ನೋದು ನನ್ನ ಕ್ವಶನ್. ಓಕೆ ಮ್ಯಾಮ್. ಓಕೆ ಮ್ಯಾಮ್. ಸರಿ ಮ್ಯಾಮ್ ಹಾಗಿದ್ರೆ. ಓಕೆ ಮ್ಯಾಮ್ ಸರಿ ಹಾಗಿದ್ರೆ. ಓಕೆ ಓಪನ್ ಮಾಡಿ. ಇಲ್ಲ ಮ್ಯಾಮ್ ನಂಗೆ ಅದು ನ್ಯೂಮರಿಕಲ್ದೊಂದು ಫುಲ್ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡಬೇಕು, ಯಾಕಂದ್ರೆ ಅದು 5 ಸ್ಲೈಡ್ ಇದೆ ಮ್ಯಾಮ್ ನ್ಯೂಮರಿಕಲ್ಲೇ, ಅದು ಪೂರ್ತಿ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡಬೇಕಾ? ಓಕೆ ಮ್ಯಾಮ್ ಅದನ್ನು